One supernova outshines billions for weeks, so why does the sky look calm? Because space is huge and empty, our view averages chaos away. The immediate takeaway is simple: the smoothness is an illusion of scale. Zoom in and you see shockwaves, jets, and ripping gravity. Zoom out and those spikes blur into a gentle background glow. Your eyes and even telescopes collect light from vast volumes. That light mixes countless events, then paints one quiet picture. Violence is frequent somewhere, but rare in any tiny patch today. Distances dim energy fast, while time stretches signals into softness. So the universe looks smooth, while the physics underneath is brutal. Tiny test, hold a sparkler far away, it becomes a hush. Net result, calm skies are a wide-angle average of turmoil. Picture a pebble tossed into a lake, ripples spread then fade. Cosmic smoothness means the universe looks similar on very large scales. That matters, because it lets us write simple equations that actually work. Space is extremely empty, so disturbances travel without crowding each other. Brightness also falls with distance, following a strict inverse square law. Meanwhile, expansion stretches light and lowers its energy in contrast. Add all three and spiky signals get blurred into a flat field. Here is a concrete sense of empty, 1 atom per cubic centimeter. Between galaxies, you get a few protons in an entire cubic meter. Your living room has quintillions more particles than deep intergalactic space, so shock fronts can cross light years and still barely meet anything. A typical galaxy hosts about one supernova every 100 years. There are hundreds of billions of galaxies, but they are far apart. At 100 million light years, a supernova fades to a whisper. Now mix many faint whispers and you hear a steady background hush. Rule of thumb, distance and emptiness smooth intensity faster than chaos forms. So the picture is, sparse matter and dimming make brutality look gentle. Watch a thunderstorm in a time lapse, the fury seems graceful. Cosmic events play out over months, years, or millions of years. So snapshots we take look composed, not frantic or explosive. A light curve turns a blast into a rounded hill of brightness. Orbits smear collisions, because gravity trades direction faster than we sample. Even telescopes revisit the same field after long, quiet intervals. Shocks expand, cool, and dim, while dust scatters the harsh edges. Radiation redshifts during travel, moving bitey photons into gentler colors. A nearby supernova brightens for weeks, then declines over several months. A pair of galaxies merge over billions of years, not minutes. Jets flicker by milliseconds up close, but average out over distance. We stitch frames across time, so the drama becomes a glide. One sentence recap: long clocks and slow sampling make violence look poised. Unroll the baby universe as a sky map, it looks eerily uniform. Inflation is a burst of exponential expansion right after the Big Bang. It matters, because it explains why distant regions share near identical conditions. Space expanded stupendously fast, stretching tiny jitters into wide, gentle ripples. Causal patches were pulled apart, so temperatures evened out like batter. Photons also diffused before atoms formed, which blurred small-scale variations. When electrons paired with protons, light finally streamed as the microwave background. That glow is uniform to 1 part in 100,000. Satellites measured bumps near 100 microkelvin, riding a 2.7 Kelvin C. Patterns match sound waves in plasma, frozen as spots and stripes. Example in real terms, the biggest hot spots span 1 degree. That is 2 moon widths on the dome of the sky. Bottom line, early physics ironed wrinkles so the fabric looks smooth. Drop into a galaxy after a messy merger, it still looks settled. Virialization is gravity trading kinetic and potential energy into steady balance. That matters, because chaos relaxes into predictable motions we can model. Stars dive and climb, and their random directions cancel net lurches. Dark matter forms a halo, where velocities mix into a stable distribution. Gas shocks, cools, and settles into a rotating disk with spiral patterns. Magnetic fields and turbulence heat the gas, then radiative losses calm it. After a merger, orbits phase mix, erasing sharp features into faint streams. Typical big galaxies show velocity dispersions near 200 kilometers per second. Yet the disk can look paper-thin across 50,000 light-years. A major merger relaxes within about 1 billion years, not overnight. So the picture is, gravity turns uproar into a composed rotating system. Step between galaxies, the nearest atom might be meters away. Space is not a stormy ocean, it is a near vacuum. Pressure waves fade quickly, and shocks mostly heat tiny dust grains. Jets aim narrowly, so most directions miss you entirely. Inverse square falloff drops intensity by 4 times every distance, doubling. Expansion steals energy too, by redshifting photons to lower frequencies. Cosmic rays zigzag on magnetic fields, spreading damage thinly over volumes. Consider a gamma ray burst, the fiercest known stellar explosion. It can release about 10 to the power of 46 joules. But at a billion light-years, the arriving flux is whisper faint. Detectors see brief spikes, while the sky to your eye stays unchanged. Example, in real terms, one burst lit detectors for mere seconds. Net result, monster energies disperse so widely that scenes look tranquil. Even when sources are bright, their faces fade in a sneaky way. Surface brightness dimming makes distant objects look softer per square arcsecond. That matters for our eyes because contrast is what shapes perception. As redshift increases, photons arrive slower and each loses some punch. Angular size also spreads light over more sky, lowering apparent glow. Put together, the dimming scales as 1 plus z to the 4th. So a galaxy at redshift 2 looks 16 times less intense. Hubble deep fields show smeared smudges, not crisp blasting fireworks. Gravitational lensing further stretches images, smearing arcs into graceful curves. Example, a lensed arc might span 30 arcseconds, with softened edges. One sentence recap: cosmological dimming edits violence into a watercolor wash. Pan out to hundreds of megaparsecs, structure starts to average away. Cosmic homogeneity means statistics stop changing beyond a large enough scale. This matters because simple models then match galaxy counts and clustering. Gravity builds a web, but long filaments crisscross and fill the volume. Counts inside big spheres vary less as more regions get included. Fluctuations cancel like coin tosses when you sum over many patches. Surveys like SDSS map millions of galaxies, revealing this calm trend. Beyond about 300 megaparsecs, density contrasts shrink towards statistical flatness. Example, counts per volume wiggle a few percent, not tenfold swings. Bottom line, the web looks busy up close but smooth in bulk. Drift over Andromeda's disk at night, the lanes look painted. Disks keep order by rotation, balancing gravity with centrifugal motion. That matters for the view because shear turns clumps into spirals. Gas clouds orbit, collide gently, and radiate heat as they settle. Magnetorotational instabilities stir, but viscosity and cooling tame the chaos. Dust scatters starlight broadly, softening hard edges into diffuse bands. Hot stars blaze blue, yet dust lanes hide the harshest cores. Andromeda turns about 250 kilometers per second, nearly flat. Its star formation runs near 1 solar mass per year, quietly. Example, giant molecular clouds span dozens of light years, yet blur. So the takeaway is, organized rotation paints turmoil as patient geometry. That supernova that could outshine billions still vanishes into the background. Vast emptiness, redshift, and averaging wrap cosmic violence in velvet. Now you know why the sky stays calm while engines roar. If this reshaped your picture of space, share it with a friend. And keep looking up because serenity often hides the wildest stories.